So take a piece of paper, draw a line across the middle of it, and our first diagram is going to fill up this first upper half, and it's going to show the Earth and the sun. And what we're going to focus on here is just day and night. So let's put a title at the top for day and night. And we will start by drawing the sun maybe over here. And we're not going to draw these the right distance or the right size. So we're just going to put the Earth over here. So the sun is the only source of light within the solar system, meaning that it's the only thing that's creating its own light. Yes, the moon has light coming from it, but it's basically just reflecting off of the sun. The moon is like a big mirror in the sky. The same is true for the Earth and the rest of the planets. So the sun is sending light in our direction, right? So we have these light waves coming towards us constantly. There is no stop to the sun sending us light. So if the sun is constantly making light and has been doing that for 5 billion years, how come we have day and night? That's what takes us from daytime to nighttime. Yeah, that's why we have that 24-hour cycle. At least now it's 24 hours long. It hasn't always been as long as it is now. It used to be that we were rotating faster. In fact, I read something recently that they think that there might have been at first only 5 hours instead of 24 hours, rotating basically what, 5 times faster almost.
That sounds a lot.
Yeah. And we think it's going to slow down even more in the future, and we'll talk about that more in a minute. But basically, we have day and night because we're rotating on our axis, because half of the planet is lit by the sun, but the other half is not. So let's fill this in over here to show the nighttime side of Earth. Does that make sense? We're going to actually look at some actual spheres we're going to turn off the lights in the room, and we're going to turn one light on in the center, a light bulb in the center, and then we're going to look at some spheres to see how they're lit up from different angles. But basically, the light is leaving the sun, it's hitting one side of the Earth, and then the other side of the Earth is in shadow, isn't it? The Earth is making a shadow. It's like if I stand, where can I stand? Oh, over here. If I stand with my back to you guys, my face is lit up, but the back side of my head is not lit up, is it? I'm creating my own shadow of myself. Huh? And the same thing is true for the three-dimensional Earth. Of course, if you're a flat earther, you probably have some other explanation that is not really supported by the evidence. But at any rate, this is what we have observed to be true. So the light is coming from the sun. Let's say if I'm a person, I draw like a little stick figure. I guess this isn't a little stick figure, it's a giant stick figure. Here's a person standing right there. Would they be in the sun right there? Yeah. So this, I don't want you to draw that. I'm going to erase it. But just imagine we're looking at what things look like from our viewpoint, huh? And if we're looking down on top of the Earth, this person would be spinning around once a day, right? Does that make sense? So here they are at noon with the sun directly over their head, huh? And then when they spin around to this side, this would be midnight, wouldn't it? They're on the dark side of the earth now, huh? Okay, so I'm going to erase the people, and I'm going to erase the circle, the arrow. So right here, I'm going to label this as number 1. And then I'm going to label this as number 2. And I'm going to label this as 3, and this is 4. Go ahead and add those labels to your diagram. And let's show an arrow circling. So the arrow is showing Earth's rotation. And we're looking down on top of the Earth. This is the North Pole right here. In the center of that circle will be the North Pole. We're looking down on it, right? From far away. And as we're rotating, if we're on the Earth, what would you experience? What time of day would it be if you're at position number 1? That would be noon with the sun directly overhead. The opposite of that, when you're completely on the far side of the Earth compared to the sun, that would be what time of day? 2 would be midnight. Now, these are not listed in order, are they? It actually goes 1, 3, 2, 4, doesn't it? But it's easy to figure out if noon is on this side and midnight's on the other side. But what does that make number 3? We're moving from daytime to nighttime. What would number 3, what would you experience right then? It could be 6 o'clock, depends on where you are on the planet and what day it is. But one way or another, you're moving from the light to the dark, so we call that. Wouldn't that be sunset? When the sun goes down, it's not really that the sun is going anywhere, is it? It's that we are spinning out of our view of it. We've moved away from being able to see it. It's kind of like walking around a corner and you can't see what was behind you anymore, huh? It's still there, but we just can't see it anymore. So what does that make number 4? As we're moving from darkness into daylight, number 4 would be sunrise. So what's the cause of these changes? We already talked about it a moment ago. What causes this? What's the cause of day and night, sunrise and sunset? Yeah. Now, can we explain that a little more? Can we make a full sentence out of that? What is it that Earth rotation does? Again, imagine a person on the planet. Here they're at number 1. They get carried to number 3. Then they're spun around to number 2. So it's not just that the Earth is rotating, but it's that we are in one place. And it's rotating into the sunny side and then into the shady side, huh? So Earth rotation I'm going to say it carries people, but it also carries buildings and mountains and oceans and animals and plants, right? It carries things on the Earth's surface. So as we're spinning around every day, we get carried into our own planet's shadow. And then we get spun around out of the shadow into the sunny side again, huh? And this takes every 24 hours today, right? In the past, like I said, it was faster. But just like if you were to spin a top, it ends up slowing down, doesn't it, over time? It loses momentum. And this is especially true because of the moon's gravity slows us down a bit more than would happen if we were just by ourselves. Are we good with that? Can I erase this? Okay, part two, we're going to call circular movement or circular motions. So for this one, I'm going to put the sun a little closer to the center. And we're not looking straight down on the sun this time. We're not looking straight down on the earth. We're kind of looking from the side, maybe a little above it, but not straight down on top of it. And so we're going to show Earth's orbit here, coming along. Maybe about to there is good. And then I'm going to draw the Earth. Leave some space between the arrow and the Earth, okay? Make sure you leave some space because we need to draw something else in there. And then this is going to come around back here and continue. So that's like Earth's orbit, right? And then let's draw the axes of the Earth at a tilt. And show another arrow that shows us spinning on our own axis. Just like I can do with this globe, I can spin it on its axis. So let's go ahead and label that. The spin of the Earth is properly called, we've already been using the word, it's properly called the rotation. And how long does Earth's rotation take? How long does it take us to spin around one time? Like I've got this globe here, and I don't know, pick a point that you can see. How long, actually we go in this direction, huh? Yeah. How long would it take for that same point to come back where you can see it again? Right now it's like 10 seconds, right? But what is it actually to make one turn? Like, let's see, where can I see? All right, I can see incline right here. How long does it take incline to come back to that spot?
24 hours.
24 hours, right? It takes a day. So I guess you guys couldn't see that. Um, one day for the Earth to turn once, huh? Which is amazingly fast. At the equator, the Earth is about 24,000 miles around, and it takes 24 hours to turn once, which means it's going 1,000 miles an hour. This, 1,000 miles an hour, this motion, if you're on the equator. Now, if you're further north or south than that, you're not moving quite as far. So for us, we're only moving at about maybe 600 or 700 miles an hour. That's all. like this. 600 or 700 miles an hour. Aren't you getting dizzy yet? It does exist. Oh, the good thing, the dizziness doesn't exist. Yeah, we don't feel it because we've adapted to it, huh? So the spin of the Earth, properly called the rotation, takes 1 day. It takes 24 hours. Right? Meanwhile, here's this orbit. And there is a proper term for the orbit. It also starts with R, so sometimes people get confused about which is which. But the orbit is properly called the revolution of the Earth around the sun. I just prefer to use the word orbit myself, but the proper term is the orbit. So how long does it take for the Earth to make one circle around the sun? How long does that take? Takes a year, right? And how many days are in a year? Actually, let's be really accurate since we're talking about astronomy now. A year, to get to this exact same spot, to leave this spot where we are right now, we're going to call this April 20. So here we are, 420. It takes us not 365 days to get back here. It takes 365 and 1/4 days to get back here. It does count because it messes up your calendar. If you don't account for it year after year, it messes up the calendar. And so we found these different ways to account for it. And do you know what it is? Yeah. How often does leap year happen? Every 4 years. Why 4 years? Because 4 times 1/4 gives you one extra day, huh? This is why we have a leap year, is to account for that extra quarter of a day that happens every single year. We just add it to the calendar every 4th year. But you know what? It's not exactly a quarter. It's a little off. So when leap year hits on a century, like the year 1900, the year 2000, the year 2100, you delete the leap year. So in the year 2000, it should have been a leap year, but they took it out to help account for keeping this even more accurate. So the movement of the Earth around the sun and the movement of our spinning, they're not locked together, are they? They're just random numbers that happened to be the way that our planet worked. And they're different for other planets. I forget which planet it is right now, but one of the planets takes longer to spin, takes longer to rotate than it takes to go around the sun. I think it might be Mercury. It goes around the sun faster than it rotates, which means a day is longer than a year on Mercury. So there's some really crazy stuff out there. Another good one is there's a planet that it rotates sideways like this. Its axis is completely tilted flat, which means, let's say that my iPad right here is the sun. That means this side is facing the sun for half of its orbit. And then it's in darkness for the other half of the orbit. Half of a year you're in light, half a year you're in darkness, except I think this is Uranus, and it's so far away that it takes 80 years to orbit the sun. So for 40 years you're in the light, but you're still spinning like this. So the sun is going overhead like that, and then for 40 years you're in the darkness. That'd be a nasty 40 years. Yeah, especially that far away from the sun. It would be cold. Okay, so a year is the orbit or the revolution. A day is the spin or the rotation. What's between the length of a day and a year? What do we divide the year into? We divide the year into months, right? And that has to do with the movement of the moon. which is really our focus today, is what the moon does. So what we're going to do is we're going to draw the moon, like maybe here, and we're going to show it orbiting around the Earth, like that. And so the moon's orbit, or the moon's revolution, takes 1 month, approximately, which is really where we got the word month from. What if you put another O in that, in the MON? Now month becomes 1 month. This is where we got the word, because it takes 1 month for the moon to go around us. It's not exactly a month. It's like 29 and a half days or something like this to go from one part of the moon's cycle to another. It depends what, well, it always takes the same number of days for the moon to go around us. It's like 29 and a half for it to go from full moon back to full moon.
Because isn't February 29 days?
February's 28 days, but then we add that extra 29th day when it's a leap year to account for that quarter day. So that's a little different. But when the moon hits, is not all, the full moon is not always the same day of the month, is it? Because some months are 30 days long, which is pretty close to 29 and a half. And some months are 31 days long. This is to add up to 365 and a quarter. And February is 28. But the moon is always 29 and a half. And so there are some cultures that use a lunar calendar. And if you do that, you need 13 months in your year. The moon goes around us 13 times in a year. And one of those is not the same length of time as the other. So you'd have to adjust your calendar again. There are still some cultures that use the lunar month and religions. For instance, Easter is based on, it's the first Sunday after the first full moon after the spring equinox. And that's why the date of Easter changes, because it depends on when the full moon hits. In Islam, they have a big feast, a big month-long feast called Ramadan. And the time of year when Ramadan happens always changes because they're using the lunar calendar and it doesn't match up with the solar calendar.
Well, it also has to do with Christ's resurrection.
Right, that's when we're celebrating Easter, but the date that we celebrate Easter always changes, right? It's been defined as the first Sunday after the first full moon, after spring equinox. Spring equinox, we talked about the seasons the other day, right? Spring equinox is March 20th or 21st. So if you have the full moon on March 22nd, Easter could be that next Sunday. On the other hand, if you don't get a full moon for like 3 weeks after March 20th, Easter is going to be much later in the year. So the date that we celebrate Easter is based on the moon cycle combined with the spring equinox. Okay, so do you have those 3 circular movements figured out? One of them makes the daytime, one of them makes the year, and one of them makes the month. Now, the other thing I want to point out here is I didn't really draw this quite as well as I would have liked to. I'm going to erase this and you don't have to redraw it, but this is really what it should look like. Here's the sun. Here's the Earth's orbit coming along here. And the moon does not orbit in the same path as the Earth. It's at a bit of an angle. So the moon orbit is something more like this. Can you see that it's a little bit off? It's not in line with Earth's orbit. So for example, if I take these two drumsticks, and here's the path of Earth's orbit, we're moving along through here. The moon does not orbit in that same angle, in that same plane. The moon's orbit is tilted a little bit like this. And so the moon is going like this while we are going this way. And of course, it's moving along with us, isn't it? So this is moving along. Here's the moon. My hand is the Earth, let's say, going here. But the moon is going above us and then below us. Does that make sense? And where this gets really interesting is on another topic we'll study next week, which is eclipses. So in order for an eclipse to happen, the moon, the Earth, and the sun have to be lined up perfectly. I pretty much drew them that way already. And what happens is the sunlight throws the moon's shadow onto the Earth. And that would be a solar eclipse. And that's why it turns dark, because we're in the shadow of the moon. But if the moon is down here below the Earth, the shadow just goes out into space and we never see it, huh? Or if it's the same thing, if the moon is up here above us, the shadow goes out into space and we never just see it. Similarly, the Earth has a shadow that goes out into space. It's always there. But the moon crosses through that shadow only occasionally. If the moon crosses through this shadow, then it gets darkened and we call it an eclipse of the moon, a lunar eclipse. There's actually one of those coming up in the end of May that we'll talk about more, where the moon will pass right through Earth's shadow and it'll go from being a full moon, it'll get smaller and smaller and smaller and smaller, and then you'll see the full moon again, but it'll look reddish. Sometimes they call it a blood moon. And then the light comes back onto it as it passes out of Earth's shadow. And that's going to happen on May 26th. In the middle of the night. To see the blood moon, you have to get up like at 4 in the morning or something. For us, if you're in a different part of the Earth, you could see it at midnight or maybe 10 p.m. or whatever. So the angles at which we're orbiting and at which we are rotating and at which the moon is orbiting are all different from one another. Here's the angle of our rotation, right? That's what you see on every globe, where the North Pole is tilted a little bit, huh? It's not straight up and down. The reason for that is because as we're going along this way, our axis is not perpendicular. Our axis is tilted. And then the moon's orbit is tilted even more than that. Okay? So there's all this wild stuff going on in terms of the angles that these things are moving. And you could figure out how fast we're moving through space too if you did a little math. Let's see. I don't know. How fast can we do this? I know this distance is, just to make it easy, we're going to call it 100 million miles. Isn't that a radius of a circle? Right? That's a radius. Which means to find how far we move through space on our orbits, we have to use geometry to find the circumference. And everybody remembers pi r squared, but that gives you the area of the circle. The circumference is pi d. So d is 2 radiuses, right? 100 million in each direction. So 200 million times pi. Let's just round it off. Pi is now 3, not 3.14159, whatever. So 3 times 200 million equals 600 million. We travel 600 million miles through space every year as we're orbiting the sun. Right? Is that okay so far? And how many days does it take us to do that? 365. So if I put 600 million, does that give me all the zeros I need? I need 600, I need 3 more, and then I need 3 more. Yep. And then I divide by 365. That's going to tell me miles per day. So we're going 164,3835.6 miles per day. But we think of how fast we go in miles per hour, huh? So if I divide that by 24, equals 68,000. We're just going to round this off to 500. That's our speed. We are flying through space right now at 68,500 miles per hour. Can't you feel the hair blowing back? Right? And at the same time, we're spinning at, what did we decide, about 700 miles an hour? And we're flying through space at 68,000 miles an hour. But do you think the sun is just sitting in one spot in space? Or is it moving too? The sun is orbiting the center of the Milky Way. And I don't even know how fast that is. So we're all involved in these constant motions. And the same thing is true if you look inside of our bodies, isn't it? Aren't the electrons orbiting around the nucleus of the atom? Every atom that your body is made of has all of these moving electrons around it. Okay, so next thing we're going to do is we're going to stop drawing for a minute and we're going to do a little demo. And so at home, I'm going to have you watch a video. Let's see. But you guys recognize what this thing is? This is actually the landing craft that they used in the Apollo missions. So this would hold 2 astronauts inside of it, and it would land on these legs on the moon's surface. Then when they had to get back, only the top half lifted off of the moon, and it left this platform behind on the bottom. So you guys at home, this is a video basically showing what we're going to do. We're going to turn off the lights. We're going to look at a light bulb with a ball that represents the moon. So please watch this video at home. I will post the link to it right now. Okay, so you guys at home should be able to do that. All right, so what we're going to do is everybody's going to have to get out of their seat. And we're going to make a little space. So you guys make some space up here. Move these tables around. And then so everybody take a different side of the light bulb. And we turn off the lights. Okay, so here's the sun. And your head is now the earth. Okay? And then each of us gets one of these ping pong balls on a little nail to represent the moon. Okay? So step up, take one of those. It's not that one. Okay, and the first thing I want you to do is just look at it for a second. Can you see that there's a sunny side and a shadow side? Like, just look down on it for a second. Do you see the sunny side and the shadow side? You need to be able to see the difference between the lit side and the dark side. Okay? Now, if this was on the night sky, that dark side would disappear completely, and you would only see the sunny side. At any rate, hold this up and line up the Earth, sun, and the moon, so you're kind of shading your eyes. You are now making an eclipse on your eye. I mean, I see the shadow on Gabe's eye, I see it on Jessica's eye. Yeah, can you see the shadow on my face of the moon? That's an eclipse. But how much of the moon do I see if I'm on this part of the earth looking at the moon? It's completely dark, isn't it? Make a quarter turn to the left. Try to set it up so exactly half of the moon is lit and half of it is in darkness. You see that? Keep the moon. Watch how I do this. I'm going to keep my hand right where it is. I'm going to turn my body. Right? So now the moon is over here. This half is in darkness. This half is lit. You see that? Can you make your ball half lit and half dark? Yeah? Should be half and half. Now go back the other way. Can you do the other half in darkness and the other half lit on your other side? Half and half. Now many people see a moon that looks like this and they call it a half moon, huh? It's not actually a half moon because it's named for being 1/4 of the way through the cycle. So this is a quarter moon, even though it's half lit. Now turn so that the sun is at the back of your head and move the ball out of your shadow. And you should see the entire ball lit. That's full moon. At full moon, the earth is between the sun and the moon. So we see the entire lit side of the moon. Does that make sense? Go back to the entire dark side of the moon. This is now called new moon. With the moon in the middle, it's hard to see it because it's lined up with the sun. So we don't really see anything. We only see the darkened side of the moon, and we call it new moon. Now move just a little bit, and you should see just one edge of the ball lit up. Do you see that? Can you make it so there's a crescent moon? You know what I mean by a crescent moon? It's an arc shape, right? Can you see the crescent moon in your ball by moving it? And try it on both sides. Can you get a crescent moon on the other side too? Where the lit side is just a little arch like this, just a little curve of light, right? Well, look at that again for a second. Look at your crescent now, but look at the shape of the dark part of the moon. Kind of like a bloated football, isn't it? If you go out here, you should get that shape, where it's mostly lit, but there's a dark crescent. You should get that on both sides. You should be able to do it both ways. Where it's not quite full, but it's more than half lit up. This is called a gibbous moon. Does that make sense? I don't know if you've heard that word gibbous or not. Okay, let's go back to new moon. And now turn to the left a little at a time. Now you should be at crescent moon. Keep turning until it's half light and half dark. That's called first quarter because it's the first quarter of the way through the cycle. Keep turning. We should be now mostly light with a crescent of darkness. That is gibbous. Keep going until the whole thing is lit up, and that's going to be full moon. Keep going. And now it's another gibbous phase, but it's getting smaller as I rotate slowly. It's getting smaller. And finally, I get to the point where it's half and half again. That's called third quarter or last quarter. I keep going beyond that. I'm back to a crescent. And it's getting smaller and smaller and smaller until finally it's new moon again. So those are the phases of the moon. We call them phases. And each phase takes about a week. To go from new to first quarter is 1 week. To go from first quarter to full moon, 2 weeks. To go to the next quarter, another week. And then to get back to new moon is that 4th week that gives us a month, huh? Does that make sense? So we're going to draw those next. We're going to draw from 2 angles, one the view from space and one the view from Earth. All right. That's right now, isn't it? All right, guys, we're back. I don't know how much of that video you got through, but we just did the same thing with ping pong balls. Each person had a ping pong ball, and we turned off the lights in the room except for a lamp in the center, and we were looking at how much of it was illuminated from different angles. And this is what gives us the different phases of the moon. So that's what we're going to draw next. And I think this time you should use the whole back of your paper. Okay, there we go. So the moon phases are caused by us viewing the moon at different angles as it orbits around the Earth. So as the angles are changing, we end up seeing different amounts of the light side of the moon. Now, of course, the same of the amount of the moon is always lit up. It's always half in light and half in darkness. The side facing the sun is always completely lit, and the side away from the sun is always completely dark. But sometimes we're looking at the nighttime side of the moon. Sometimes we're looking at the daytime side of the moon. Sometimes it's half and half. And so what we're going to draw is the view looking down on top of the Earth, Moon, and Sun, on top of the North Pole. And we'll see the angle that we're looking at the moon change during the different parts of the lunar cycle during a month. And then we'll also draw what it looks like from our viewpoint. And I want to make sure that I have enough room for this, so I'm going to erase this at the top when you're ready. We good to go? Okay. So I'm going to put the sun over here, way on the side, because what we're really interested in is a month. We don't need the whole year anymore. Then I'm going to put the Earth here. And remember, this is the North Pole. We're looking down on top of the Earth now, right? Looking at it from above. And of course, the lit side of the Earth faces the sun. And then we have the night side of the Earth on the other side, right? Meanwhile, the moon is going around us. And so we're going to draw the moon in 8 locations to show its orbit around us. So here's the first one. Once again, it has a light side and it has a dark side, right? Because of where the sunlight is coming from. You will see that the light side is always on the left of this diagram because that's where the light is coming from the sun, right? Now, if you're standing on the Earth here, looking at the moon, how much of its light side do you see right now, the way I've drawn this? You see all of it, huh? So what phase of the moon would this be? When you see the entire circle of the moon, we call that the full moon. So here we have full moon. And what we see, we're going to draw here next to it, is the entire circle of the moon, right? And if you want, you can draw the man in the moon, the Maria and stuff in there. But we see the entire moon lit up, correct? Full moon. Let's go to the opposite side. When the moon is over here, once again, the left side of the moon is lit up because that's the sun side of the moon. So now it's the completely darkened side of the moon that's facing the Earth. So what do we see then? If it's the completely dark side of the moon, can we see it at all? We can't see it. So this is called new moon. This is where the cycle is considered to begin, is with the new moon. And we'll just say that we can't see it at that stage.
You can see it a little bit, but not.
Well, it depends. If it's exactly at the moment of the new moon, you can't see it at all. But then you start to see a little crescent, huh? But by the time you're seeing the crescent, it's no longer new moon. It's now crescent moon. So the crescent moon, so the full moon is really only like one moment. It's gradually getting bigger and bigger, and then it becomes smaller and smaller again. We notice it for pretty much a whole night, but if you were to watch closely from moon rise to moon set, you would see that the shape of the moon changes just in that much time. So it's constantly changing, and it passes through this moment of new moon when it's completely darkened and you would not be able to see it. Now let's go down here. Once again, the same side of the moon is dark, and the same side is light. The left is dark, and the right is light. don't like the way I drew that. I'm going to do it over again. That's better. So again, the left is light because that's where the sun is, and the back side of the moon away from the sun is in darkness. But when we're looking at it from Earth, you don't need to draw this arrow, but this is where we're looking at it from. What do you see? You see half of it lit and half of it dark, huh? Yeah, we see it half and half. Now, you would think this would be called half moon, but it's not named for the amount that you see. It's named for how far it is through the cycle. And can you see that we're 1/4 of the way from new moon to getting back to the highs, to the full cycle? So this is called first quarter. It's 1/4 of the way through the cycle, but you see half of the moon lit up. So let's draw what we see there. We should see, wait a minute, I'm looking from the Earth at the moon, huh? So I'm actually seeing the other side of it lit up here. The right side of the moon is lit up at first quarter. This is what you see. And let's do the opposite side from that. Here's the moon. Once again, the left is in light and the right is in darkness. Looking at it from Earth, don't we also see half and half? But now this time, it's the left side that's in light from our viewpoint. And what do we call this? If this was first quarter, this one would be, actually full moon is second quarter. So that makes this one be third quarter. This one has two names, third quarter or last quarter. Now the ones that go in between. So right here, let's go ahead and draw. Same thing. The moon is still a full circle. It's still half in light, half in darkness. It's still the same side is lit versus dark. But what do we see? Because we're looking at it from an angle, we see more of the darkness than of the light, and we see this shape. It's so dark that it just blends in with the darkness of space. And it just looks like it's a crescent moon, isn't it? So this is crescent. And down here, same story, right? We're looking at more of the dark side than we are of the light side. So once again, we see a crescent down here, but the difference is that it's a crescent on the other side of the moon. It's now a crescent on the right side, like that, instead of a crescent on the left. Well, as we move along, between the quarter moon and the full moon, now we're seeing the opposite of the crescent. We're seeing it more lit than we are seeing the darkness. And so it's kind of shaped like a warped football. Kind of like that. Let me do that again. So you start at the top, draw a circle to the bottom, and then kind of take a shortcut in your circle to go back to the top. And that's how you draw this shape, which is probably the least familiar name to you. It's called gibbous moon. I don't know where that word came from. And this is a gibbous moon on the right side of the moon. To finish everything off, we need to do our other gibbous moon, but now it's on the left side that it's the full circle, and on the right side where we've kind of cut it off. Let's add arrows showing the direction of its orbit. And then there's one more topic here we got to fix up or add to this. How can we tell which crescent moon it is? Is it the crescent moon that's growing bigger, or is it the crescent moon that's getting smaller? Well, one way you can tell is whether it's on the left or the right, but we have these two words that describe it. Do you know what they are? Yeah, perfect. They both start with W. One is waning, and the other is waxing. If something is getting bigger, like this is on this side of the chart, this is all waxing. It's growing. It's getting bigger and bigger every day. Call this waxing. For this first half from new moon to full moon, it's a waxing moon, which is where we are right now. Today, we're somewhere around here. We're almost to full moon, but not quite. It's waxing gibbous today. Then when it starts shrinking down again, we call it waning. It's getting smaller every night until finally it hits new moon. And this is how we can tell the difference between which crescent it is and what's coming next and what's already happened. Waxing crescent is growing bigger every night. Waning crescent is growing smaller. So we should put our little definition of waning means that it's shrinking. Okay, so there's one more thing I want to talk about the moon today, and I think the best way to do this is to look at a video. So the wild thing about the moon, and here's a globe of the moon that I borrowed from Mr. Resney, and we can see on this side of it, we can see the Maria. And the crazy thing is, when the moon orbits, let's say this is the sun again, when the moon orbits, the side with the Maria is always facing us. We always see the same side of the moon all the time. We never see the back side. It so happens that the moon always keeps that side towards us, so it does rotate, but it rotates at the same speed that it orbits. So as it's going around the Earth, it always has this same side facing us, if I'm on the Earth, but out there in space, it's actually turning around, isn't it? Does that make sense? So every part of the moon gets sunlight at some time. Every part of the moon goes into the darkness at some time. There is no such thing as the dark side of the moon. But there is such a thing as the far side of the moon. The near side always faces us. At full moon, it's completely lit, huh? Yeah, this is a very interesting question, is how has this happened? We think what's happened is because of Earth's gravity, the speed at which this is rotating has slowed down so much because of Earth always pulling on it, and the tendency for like a top is going to slow down. As it's spinning, it's going to lose momentum. This used to be going really fast. We could probably see all of it back in the early days of the solar system. Like when I was saying, we were spinning it once every 5 days or 5 hours. We had a rotation of 5 hours at one point, and it's slowed down to 24 now. This is also slowed down to the point where it's now 29 and a half days. And what we probably think is that there might be more mass on this side of the moon than this side. And so that more massive side is pulled by gravity towards the Earth all the time. At the same time, the moon's gravity pulls on Earth's water. And this makes the tides, high tide and low tide, are caused by the moon. The gravity actually pulls the water towards the moon to raise the tide up. And we'll talk about that more a different day. But this video that I want to look at briefly talks about why we have these, why the same side of the moon is always facing us. This one. How do I share the sound?
We share the video on it after.
Include computer sound. There it is. Ouch.
Yeah. Okay.
What if the moon merely rotated? We here on Earth would be able to look up and see all sides of the moon, right? Of course, Earth spins too, but to simplify our discussions, let's hold it still for now. Also, let's add a yellow line so to make the rotation of the moon more apparent. Note that as the moon rotates, the line goes from vertical to horizontal to vertical to horizontal and so forth. That means it's rotating. What if the moon didn't rotate and it only revolved around us, like this? We'd still be able to see all sides of the moon, right? What if the moon both rotated and revolved? How about like this? Look carefully and you'll see that, yes, we still get to have a 360-degree view of the moon. No hidden sides. But what if the moon rotated just as fast as it revolved? Like this.
Revolve means orbit, right?
Check this out.
It's rotating once for every orbit.
Look at the line. If you don't believe me, vertical, horizontal, right? But it's rotating at a rate that matches the revolution. Just so that only one side of the moon ever faces Earth. And that's exactly the situation we find ourselves in today. The only side we ever see, we call the near side. The side we don't ever see, we call the far side. Actually, the first time we ever saw the far side was from photographs sent by a Russian lunar spacecraft in 1959. But no human ever saw the far side directly until the Apollo 8 mission in 1968.
It doesn't have as many Maria
Why
as the
don't
near
we,
side.
here on Earth, ever see the far side? Why does the moon spin exactly as fast as it revolves? Good question. I mean, very good question. We could spend weeks studying this one question. But I'll just give you the quick explanation. For starters, let me tell you, it's no coincidence. Earth's gravity gets weaker with increasing distance, right? Yeah, but over the distance of a few meters or even kilometers, this difference is not that much. The Earth's pull of gravity on your head is, for all intents and purposes, the same as it is on your feet. The moon, however, is thousands of kilometers wide, so the near side of the moon experiences a significantly stronger gravitational field from Earth than does the far side.
The size of the
What
arrow
this means
shows
is
the
that
force
the
of
moon's
gravity.
center of gravity relative to Earth is not the same as its center of mass. Center of gravity? Huh? The moon's center of gravity is the point upon which all of Earth's gravity appears to act. You could scrunch the moon to the single point, and gravitationally speaking, there'd be no difference. If Earth's gravity acted uniformly across the moon, the center of gravity would be the same as the moon's center of mass, which is the average point of the mass of all the atoms within the moon. Yeah. But because Earth's gravity is stronger on the near side of the moon's center of gravity is shifted toward the Earth, like this. Now, the moon's center of gravity can be considered to be the point upon which the Earth tugs. If the moon rotated a bit faster or slower, the center of gravity would be lifted away from the Earth. And you know what happens to things lifted away from the Earth? And that's right, they're pulled back down. The Earth would apply what we call a torque, which would align the moon right back to a position where the center of gravity is directly below the center of mass. Kind of like this. This is what prevents the moon from rotating any faster or slower than it does. The moon can only rotate so fast because Earth won't let it do otherwise. As a consequence, the moon rotates only once for every revolution, and only one side of the moon ever faces us. The differences in Earth's gravity between the near and far side of the moon has other effects as well. For example, it has the effect of stretching the moon into a somewhat oblong shape. This happens because the force of gravity isn't applied uniformly. Earth's uneven gravity acting on the moon causes an oblongish deformation. Remarkably, the moon has the same effect on Earth. This is most noticeable with the Earth's oceans, which are relatively easy to stretch. As the Earth rotates beneath this oblong shape,
So
the
here's the
sea level
tides.
goes up and down. As we pass under each bulge, we experience high tide twice a day because there are two bulges. The two low tides are when we pass under the narrow regions of this oblong distortion. This oblong distortion tends to hold the oceans still relative to the moon. So there's actually a bit of friction between the ocean floor and the water as the Earth rotates. This friction, combined with a small torque on us by the moon, is slowing our rate of spin. As I said earlier, back in the time of the dinosaurs, a day was about 19 hours long. In a billion years or so, a day will slow down to about 46 hours. At that point, only one face of the Earth will face the moon, much like only one face of the moon now faces the Earth. By the time this happens, the moon will be much farther away because of the conservation of angular momentum, which we haven't talked about. But like a fast spinning ice skater, slowing down needs to throw her arms outward. The moon, slowing down Earth, can only do so by moving itself outward. Then the Earth and the moon will be completely locked in their dance around each other. Right now, the Earth is kind of shy and always turning away from the moon's constant gaze. But when Earth finally returns that constant gaze, when we're finally completely locked together, the moon will appear at a single location in our sky, day and night. People on opposite side of Earth won't ever get to see the moon unless they go on vacation to the moon view side of our planet, where I'm sure real estate prices will be higher, along with the sea level, in a billion years from now. Will still be around? Oh, I got a question for you. Does the far side of the moon ever see the sun? Think about that. Oh, and can you ever see the Earth from the far side of the moon? Lastly, if you were right here and you looked straight up, what would you see? Would it ever stray from being directly above you? Ooh, good questions. Good science to you.
All right, so how are we doing for moon phases? Does that make sense? How the movement of the moon around us, we look at it at different angles. So that gives us the crescent moon, the quarter moons, the full moon, the new moon, and the gibbous moons, right? Okay. I'm going to ask you to take photos of your diagrams and upload them. I haven't made the assignment yet. So it'll only take me a couple minutes. I'll make an assignment and then you upload your photos and you'll get points for your participation today. And then we should be able to label diagrams like this on a test. Okay. And you have the rest of the period to finish the moon mapping assignment we started. Basically, we're only doing the map of the near side of the moon that faces us. We're skipping the far side of the moon. But I'm going to pass this globe around so you can look at it. It has the locations of not only US landing sites, but there's some Russian ones here too. Soviet, I should say. It might just be the first one.
Yeah, like you said, Americans are the only ones who walk on
Yes, the unmanned landings. Yeah, here's a Lunik 2, 1959, first unmanned landing.